take care of the interface to get a good quality of building a transistor. And you are making zillions of transistors, so you have to have a very, very clean interface. And what is the advantage of oxide? Because Mother Nature helps us. One monolayer, one single layer of side stabilizes that interface by at least 2 orders of magnitude. 2 orders of magnitude. At least 2 orders of magnitude. So from high 10 to the 12, you're down to 10 to the 10. Just one monolayer of oxides. Just think how important that oxide is. Okay. So, and then we do other tricks to bring it down all the way to 10 to the 9 per square centimeter level, where then it's not significant anymore and you can do the device size. Okay? So, the trick of the trade is that the second one, from field effect transistor point of view, interface properties are extremely important on an atomic level, and oxide does the trick. Now, it so happens that nitride in a very monolayer stage is also very good to do that. So, and as we scale the oxide, nitride adds to the strength of the dielectric and reliability to the dielectric, as long as it's not thick enough to create bulk traps of its own. The trap density in good quality oxide is extremely low. Strapping cross section is very large. Compared to nitride is far worse. But nitride has a very good passivation characteristics. So the nitride oxide has been used for almost from 1990 to 2000 plus as a way to scale the so-called gate oxide thickness down. But then after that, you had to go into high gate-dielectric because leakage, as you thin it down farther, leakage is a very important consideration. And you need the gate capacitance large so that you can reduce the threshold voltage, scale it down. So since 2000 and prior to 2000, almost 20 years, the industry knew that there would be a limit to the oxide. We can scale it down to a certain point and then can't do anymore. So industry had started looking into high gate-dielectric, and any material perfection to atomic level takes a lot of effort, a lot of time. So it's not a simple thing, because you're talking about all kinds of parameters. And that reminds me, I may give you a special lecture on insulators, very thin film insulators. Remind me, I'll put that together for you, so you can understand and appreciate what the high gate-dielectric insulators. In fact, I mentioned that too, at least partly in that book that I wrote, because not non-volatile memory detection. Anyway, so here I answered those questions: isolation and interface state density control. What's the third one? Third one is you already mentioned. That passivating oxide. The passivating oxide, which helps us to identify the region that we are going to put active device, the region that we are going to keep it passive, keep it isolated, etc. And that's pad oxide, and typically the pad structure is an oxide nitride structure. It's a question of printability, etchability, identifying, it starts at the very beginning of the process so that we can identify everything, the piece of paper, uniquely and do all kinds of alignment aids into that. That's it. So those are the three most important And I think I already covered. Can you go? All right. Yeah. So you can see, here's the gate, so you have a gate oxide. Here's the so-called isolation oxide, which is the low-cost type of isolation. Nowadays, low-cost is all replaced by shallow trench, actually, it's STI. So we go more vertically down. We don't have this nutty problem called bird's beak. The way we used to make this oxide isolation is put a layer of oxide and nitride, and the nitride creates stress right into the oxide. It lifts it outside, and then it creates this wide region which not only create a problem of reducing the isolation size, but it also creates some defect problem of the dielectric. So we eliminated that. No longer you see that kind of isolation. It's gone almost 2 decades. Then what's else? And of course, I identified earlier that these are all isolation here. These are all oxides here, the so-called passivation oxides. Okay, whatever you see, kind of open white region is all oxides. So you have those rows of oxides in separating the contact from the gate, and you have other things like wiring, polycrystalline wiring, polycrystal doped polycrystal, which is a conductor, very heavily doped. So you have the wiring that's going next to each other. Now, you remember what I mentioned to you. If you look at these structures, everything primarily is capacity. There's a capacitance here to here, there's capacitance here, there's capacitance between nodes to nodes, everything. It's all capacitive loaded. Primarily the main technology is all capacitive, primarily. There are other elements, resistive, inductive. Inductive is particularly so when you do a lot of logic technology where you have a lot of wiring, many levels of wiring. So you have inductive load. But by and large, internal to the device, mostly capacitive. Okay, let's move on. So, you know the importance of isolation. We have already spoken to that, right? We do not want any form of leakage of any significance because the isolation, when you're on the wiring level, your isolation is sitting next to the active device, right? And so you can see that the isolation is act like a thick oxide gate, field effect transistor. It's a parasitic device. It's a parasitic device. So, if you don't design that properly, you can introduce during operation a certain amount of leakage of this, because it's also acting like a parasitic field effect transistor, sometimes in series, sometimes in parallel to the circuits. So, you have to make sure that no parasitic effect of any significance takes place to make an effective isolation, which means that even the worst situation, the leakage through that parasitic device would be at least 3 to 4 orders of magnitude lower, at least 3 to 4 orders than your active device. Okay. So you do calculate what the worst case parasitics due to the isolation would be, and ensure in the integration of devices design that you have met all that requirements. So that's the importance of isolation. And you can see, right? Transconductance, VDS minus V threshold. You want to make that threshold very high for parasitic devices. Okay? That's why you make it thick. Why do you make it thick? Because now, in most technology, they actually put a little bit of dopant right below. They enhance the doping boron, like p-type silicon, where you were starting material. The pad structure, right after the pad structure, you do implant a little extra boron below that pad structure, which will generate into the, where the STI is going to be. So right at the bottom of the STI, there is a higher dose of boron. And why is it? What does it do? It's higher than the substrate doping level. Why does it do that? Why do we do that? Can anybody answer? Can anybody answer that? What does doping level do? That's directly tied to threshold, right? Go to the basic current equation. So, threshold. So, you want to lift up this threshold. The more you lift it up, the current is lower of a parasitic device, which is your isolation limit. For the parasitic device, you're making it harder to turn on, even in the worst case scenario. You're making it difficult to turn on. And the reason you do that is because you want that isolation to be truly isolation. There will be zero leakage. There's no such thing as zero, so it will be very, very small. Negligibly small, so you can design your circuits without any problem. Right? So that's the importance. Charges has to be low, because charges lift up the thresholds. Interface charge has to be very low, as we spoke about how important interface charge is. Mobile charge and trap charge. All these types of charge is progressively reduced and eliminated to learn the FET technology. When I first started the technology was developed as a prefab technology. P-channel FET. And the reason is, can you tell me the reason? In the P-channel technology, the threshold is negative. It's always conducting. And if you have one of the major contaminants like sodium is everywhere. Even when you use the purest chemicals, there is also a certain parts per million of sodium. And sodium is a mobile ion. It's very easily moved. If it goes to the interface, the prefect, it doesn't bother, right? Because it's a positive charge. But now you turn around and try to do MFET. That is going to raise the threshold. And not only that, it moves with the field you put it in the gate, right? So it depends on what is that you put in the gate potential. So sodium can move all over the oxide, very readily mobile, even at room temperature. So your threshold shifts, and that's not a reliable device. So when they tried to, people always knew in the early days, if we can make MFET, we get higher performance. Why? Tell me. Mobility. The electron is the current, right? Not more. However, they ran into the nutty problem of changing the mobile charge. Now I had my little lab by that time. I had it all set up. We were all excited to go on that. So I was scratching my head and said, how do I control this mobile ion? Because I want to build MOSFET. The R&D center in IBM, Watson Research, they were only building PFET. I was not happy with that. I got to build MOSFET. Then there was a very good designer who ended up being an IEEE president one time. And he was espousing MOSFET circuits. And he was showing all this. This is his own research. And he was saying, our future is MOSFET. And the little lab in our research center, we're only doing PFET. So I said, I'm going to build MOSFET. I'm going to build MOSFET. I'm going to show them that MOSFET can be built. And I'm scratching my head. What do I do? So if it is sodium, I said, that's all that people keep saying. I'm going to get rid of the sodium. I have to make sure it doesn't enter the furnace when it goes oxide. How do I do that? I came with this idea and went to my management. So I need chlorine gas. Sodium chloride, very stable. You all need sodium chloride, right? Salt. We can survive without salt. Our brain, sodium ion moves all around. You know, triggers your thinking. Just think about that, right? So, they fell off from the chair.